Okay. Hi, my name is Tami Norton. I work for a company called Ecosystem Planning and Restoration. Let me start it. We good? Okay. Again, my name is Tami Norton, and I work for a company called Ecosystem Planning and Restoration, also called EPR. We are just like our name says, an ecosystem planning and restoration company. That's what our specialty is. And LeeAnne and I we're both water resources engineers. We are in the San Antonio office of our company, and we are very happy to be able to present to you tonight and show you some of the things that we do. So we would like you to get out of this presentation to be able to understand the correlation between stream condition and behavior of natural stream processes, and also identify current practices that are being done and things that we might be able to do to improve stream functions, and also to manage impacts to streams through practices that require less maintenance. So we will be talking about natural stream functions and processes, channel instabilities, and we have a local case study to show you, and we'll do questions and answers when we're finished. So one of the questions that we like to ask, and it kind of depends on who you are and your worldview and experiences, how you answer this question. So what is the function of a stream? Well, if you're an engineer, you might say it's to move water. It's to get flooding and stormwater out as quickly as possible. If you're a geologist, you might say, well, streams move sediment and they help shape the landforms. If you're an ecologist, you may think, oh, streams are habitat for aquatic animals and fish. And all of those answers are correct. Oftentimes, projects get kind of tunnel vision depending on who's put out the project and what the goals of the project are. But we like to think of all of these things when we think of a project. So stream functions, when we talk about stream functions, we also include the floodplain, not just the channel, but the floodplain that conveys the larger flow events. These systems, they do transport water sediment, they provide flood storage, sediment storage, they provide that ecosystem structure for plants and animals. Sometimes they even recharge the groundwater, and they have a lot of water quality benefits. So when we think of streams, we kind of zoom out. The first thing we want to think about is where are we in the watershed? Different streams will behave and have different characteristics depending on where you are. So if you're up in the headwaters, you might have a steeper, more steep stream that has a different shape and different plan form than a stream that's down in an alluvial valley where it's flat slopes and you have this nice meandering stream system. So whenever we look at a stream and we're looking at a potential project, we need to think about where are we and what kind of stream is appropriate for this site. What should it look like? What does it look like? And what can we do with it? The letters that are on this graph, they are in reference to what we call the Roskin stream classification system. And this is just a tool that we use in our industry to communicate what kind of stream we're talking about. So for instance, if we say this is an A stream, people that are familiar with the classification system will know, oh, A stream, that means it's a headwater stream. It's up in the mountainous areas, it's a steeper slope stream. Or if somebody says, oh, I'm looking at a C stream, we know, okay, that's got to be in an alluvial valley and it's probably a meandering stream. So it's a good communication tool just to talk amongst ourselves, so to speak. And so we know what we're dealing with. This is another representation of that same classification, but it shows in profile what these kinds of streams look like when we say an A stream, B stream, etc. It shows a typical kind of cross-sectional view of the kind of stream that we're looking at. And then also, what does it look like in plan view? So what are the patterns that we're seeing? So A and B streams are straighter streams, they're steeper slopes, whereas a C stream and an E stream are flat slopes, meandering systems. D streams are degraded systems, multi-channel systems, and then we have Fs and Gs. And in our world, especially in this area, when we hear that a channel is an F or a G, that sends flags that that channel has problems. Fs and Gs are generally unstable in this region. So that is how this classification system is useful for us. So stream dimensions are really important. And depending on, again, where you are, what kind of stream you're dealing with, what kind of valley type you're dealing with, these dimensions they're an actual physical, mathematical dimension that is formed by physics and natural processes. And it's universal, it's worldwide, it's not something that's specific to a region. And these dimensions are based on the size of your watershed. So drainage area is really important to know. What kind of land use is going on in your watershed and near the stream system, what kinds of vegetation are present or absent, the type of soil and the geology, your topography, again, is mountainous, flat slopes, and then of course your climate will vary from place to place. But all of these things determine the dimension, a stable dimension for a natural stream to function properly. So our goal when we design is to figure out what is that dimension? What is going to be a stable dimension for our stream, for our location? Some typical stream patterns that most people are familiar with are meandering stream systems. These are the squiggly ones, the ones that are in alluvial valleys. They're generally broader streams. They're down in the watershed, not necessarily at the downstream end, but they are definitely beyond the headwater point. And meanders actually serve a purpose. They are natural energy dissipators for floodwaters that come through. So as the flow comes through and it meanders through these bends, it slows the water down. You get scour pools. Let's see, can I use this? I don't know if they can see this on Zoom, but I'm gonna try to point. No, okay. So scour pools form at the point, at the inside of the bends, or the outside of the bends rather, and then point bars form on the inside of the bends. And they're very important. So basically their energy dissipation horizontally as it moves downstream.
Your cursor just
okay. If I need to do that, I'll do. Okay. So in profile, a meandering stream looks like profile A on this slide. So you have a series of riffle and pools and some other features called stream facets that not only provide a hydraulic function, but also provide habitat. So for instance, fish often like to spawn on riffles, and different critters like different parts of the stream for where they live. In a straighter, steeper stream system, instead of energy dissipation horizontally, it dissipates energy vertically. So you get a series of steps and then a pool, and then a step and then a pool. And that's how the stream naturally dissipates that energy and keeps that balance. So you don't get a stream that's eroding or degrading. I don't know how many of y'all have seen a lanes diagram before, but it's another useful tool for visualizing impacts to a stream. So, and I'll talk about this in a little more detail in just a second, but on the right-hand side, you have stream slope and you have water quantity. And on the left is the sediment size and the sediment quantity. And essentially, if you change any of these parameters, this lanes diagram will help you predict what your stream, how your stream is going to respond. So even it doesn't matter if we've come in and we've engineered a channel, natural stream processes are always at work. And if you are trying to do something that goes against natural stream processes, you're going to know, because you're going to see your stream start to change and try to come into equilibrium again. So this is a local example. This is San Pedro Creek. It was channelized several years ago for flood control. Originally, it was a trapezoidal channel with a flat bottom. And over time, you can see that a low flow channel has developed. And we are starting to see that meander bend process happening. We get erosion on the outside of the banks and deposition and point bars forming on the inside of the banks.
where on the creek is it?
That is just upstream of I-35, I think. I think it is. I think so. I can't remember exactly where this one is. I can see downtown.
I think you're right.
Like Provet area, like heading towards Provet.
It's
Is it center or just on the west side? I think it's on the far west side. Yeah, with the tower there.
Okay, well,
Yeah.
it's in San Antonio. I've seen some of these, they all look the same to me, so, okay. This is another example of a channelized creek that was probably put in when the subdivision was developed, and most likely it had some meandering to it, given the slopes in here, and they've come in and they've straightened the channel. And I'm sure that this was a trapezoidal flat bottom channel, and over time, this low flow channel has developed, and you can even see that it's trying to meander again by the flow vectors. And over time, if it's left on its own and there's no maintenance done, it will start to meander. You will start seeing erosion and the changes. Yes, sir.
We're talking about the trapezoidal bottoms. We're talking about the concrete channels that are inserted on the bottom of this one.
Sometimes they're concrete, sometimes it's just the shape.
And can you just repeat the question for the people on Zoom?
Okay.
Because they didn't.
The question was, are we talking about, when we say trapezoidal channel, are we talking about concrete bottom channels? And the answer is they could be concrete. A lot of them are completely concreted. Some of them are not, they're just grass lined. And I suspect this one was just grass lined, and nature does its thing, whether we want it to or not. And I'm sure over time, if this is left on its own, these neighbors will get pretty upset when the creeks start to encroach on their property. So maintenance is an issue for these kinds of streams. This one more example, it's another flood control channel that you can see that the riffle pool system is starting to develop all on its own. So what are some of the impacts that causes the channel to respond this way, other than just the channelization type of thing that we just saw? So there's many things that can happen to a channel that are direct impacts, meaning it happens to the channel itself. There's dams that are built, dock tanks, inline dock tanks, big dams, big reservoirs, again, channelization and levees. Some places there's mining that occurs even in the main stem, or even off in the just to the side, has impacts to the stream. Some places there's beaver activity, and either the beaver have come in and are starting to disrupt, or the beaver are taken out, which can also cause problems when the beaver leave. We don't have that problem here so much, but in other places it is a big issue. Point source discharges, those are like stormwater outfalls from storm drain systems, just dumping stormwater straight into the creek. That could also include, what am I trying to think? The wastewater treatment plant discharge locations as well. Floodplain encroachment is a big one. Folks like to squeeze the creek corridor as much as possible to gain as much land for development as they can, and that has a major impact on streams. Snagging and wood removal. There are agencies that do that, and the primary purpose is to keep flow moving. There's a flood control component usually involved, but the wood in the stream actually plays a role in natural stream processes, mostly habitat wise, but it is important too. And then of course, urbanization, we get lots of road crossings, utility crossings. Those crossings themselves, you see a lot of issues at some of those crossings. And then in the ag world, livestock having access to the channel is a big problem. Cows are pretty devastating to a stream in terms they beat up the banks, that kill, they eat all the vegetation, and then the water quality becomes pretty nasty. So direct or indirect impacts are things that are happening outside of the creek. So what's happening in the watershed around it? Agriculture is a big activity that takes place. There's forestry and tree harvesting that occurs. Urbanization is the biggest impact. And then along with urbanization comes road density. So here's the lanes diagram again. So to demonstrate how this works, let's say we have an impact. Say somebody comes in and they want to straighten the stream. Well, when you straighten a stream, you steepen the slope. Or maybe they want to put in a storm drain outfall that adds more flow to the system that was currently there. you can predict if you increase the slope or increase the water, you're going to see that stream start to degrade. That means, and degradation indicates erosion, material being moved, the channel changing shape. The other way is, let's say somebody dams up the stream upstream and suddenly you don't have a flow that you used to. You will see aggradation is something you can predict will happen in the stream because the stream has lost the power to move the sediments that are in the stream. It can no longer pick up the same size sediment load that it did before and move it. So you're going to start seeing it fill in. So this is a cool diagram to help you predict if this happens, this is probably going to happen. If this happens, this is probably going to happen. Some of the causes of instability we've already talked about. Increasing the slope is a big issue. Increased runoff into your stream, changes in the sediment, either the sediment load or the size, loss of riparian vegetation, and that riparian corridor is a big issue as well. And then loss of floodplain areas. So this is a demo, just kind of a demonstration of, so let's see what happens when you channelize a stream. We have a nice, pretty blue meandering stream, and someone wants to channelize it for some reason. And the brown line is the channelized new streamline. So we are getting from point A to point B much quicker, shorter distance. And when you do that, you increase the slope of that channel. Well, the channel is going to respond, and it will respond until it finds what we call equilibrium slope. That's a word for me to say. And essentially, you'll start seeing the stream degrading first. Means you'll start to downcut. It'll go through a series of evolution processes, is what we call it, channel evolution. It'll start to downcut. It'll reach a point at where it stops downcut. It'll start to widen, and the banks start to fall in. And then that sediment gets moved downstream, and eventually it will come to this equilibrium slope. So sediment that is scoured out upstream is deposited downstream until eventually the stream picks the slope that it likes. And it can be a very destructive process and an expensive process to stop from happening. So when we do stream projects, these are things to think about in terms of maintenance. If I do this, what is the stream going to do? And what am I going to have to do to stop it from doing that? Increased runoff. Primary increased runoff reason is increase in percent impervious due to urbanization. When you increase your paved areas and your impervious areas, you increase your runoff. So this kind of explains generally what happens. If you have a natural ground cover, about 50% of the water will infiltrate and about 10% will run off, and then you lose some to evapotranspiration. Once you get to 75 to 100% impervious cover paved areas, you may only have up to 15% infiltration, but 55% runoff increase. And that is a big deal, because this is another way to look at it. The dashed line is, these are hydrographs, and they represent a flood flow coming through a system. So the dashed line is a rural pre-developed hydrograph, and it starts to rain, flow infiltrates, it reaches a point where it starts to run off, and then you reach a maximum peak flow, and then you have the falling limb of the hydrograph, and it goes back to its normal condition. When you come in and you pave, suddenly you don't have that water that can infiltrate. So you get a huge rise in runoff immediately, and that peak is higher and your flood volume is higher. And then eventually it will go back down, but your stream has to absorb those changes, which is a big deal. Increases in sediment load can be from different things. Any changes out in the overbank that causes soil to loosen and be able to make it to the stream can be a source. Agriculture, often you'll see loss of soil due to agricultural practices. During new development where they come in, they clear out all the vegetation, you'll see soil entering into the system that wasn't before. A decrease in sediment load, that can be due to somebody installing a stock tank or an inline pond. Suddenly you've stopped not only the flow, but you've stopped the sediment from being able to continue down the stream system. Loss of riparian buffer. This is where the vegetation comes into play, and it's very important. This is a ranch that's south of town. I can't remember where it is, but we visited them several years ago to come and look at this issue that they're having. So the rancher has pretty much wiped out any sort of vegetation other than the grass for his cattle. The cattle also have access to the creek. That creek is still there. And he started having what we call head cutting. So there's a nick point. The water is flowing towards us in this photo. And there's a little waterfall that you can see that is called a nick point. And that is a head cut. And that is the current face of where the erosion process is happening. So if it's left unchecked, it will continue to go upstream and create a canyon through this guy's branch. Right now, if he were to stop the head cut, do some treatment to stop the head cut, he could probably replant upstream, and that would take care of it from continuing upstream. But if he didn't do anything about it, he's going to have a canyon through his ranch. This is an example. There's some cows in the top of the photo of what cows do to creeks. They stomp the banks, they eat the vegetation, and they use the creek for things they shouldn't be using it for. And the water quality gets pretty low. So some of the current things that people do to try to stabilize unstable creeks right now are typically, let's fix it in place. We've got a bank that's eroded, it needs some sort of fix. They might resort to hardening, like putting in concrete on just the bank. They might concrete the whole channel. They might use gabion baskets or something like that. Sometimes those things are sufficient to fix the problem, sometimes they're not. If it is a localized instability, this might fix it. But if it's a reach problem, this is not going to fix it. They're going to be coming out here and fixing these things over and over again because the stream, you're fighting against the natural processes of the stream. Vegetation management, again, these are some, one is a park and the other is just a drainage way that's maintained for flood control. Common practices are to mow right up to the edge of the bank, get rid of any sort of riparian areas because they don't want to take care of them. It's cheap to maintain that way. But when doing that, they start having a maintenance problem in terms of erosion. So this is where vegetation management comes into play. And there's a lot of reasons why people don't want to have a big woolly creek in the middle of an urban area. There's plenty of reasons why that is something that's undesirable. Some people don't like the way it looks, number one, they like this. Some people don't want trash that gets hung up in the vegetation in an urban setting. And some people don't like nefarious activities that take place in wooded areas in their backyard. So there are reasons, but there are ways to manage what kind of vegetation goes in, how tall does it get, how wide is it, those kinds of things where we could come to some sort of compromise to not end up with that. And when a creek erodes upstream, that sediment gets taken downstream and deposits somewhere. And typically you get deposition and sediment accumulation where across the cross section of the stream widens all of a sudden. So it loses stream power. And you'll see this a lot of times at bridge crossings where you have a creek that's like 10 feet wide normally, and all of a sudden you've got a bridge crossing that's 100 feet wide. And that's typically to pass the 100-year flow. But when you do that, it loses all the stream, loses all of its stream power, and all the sediment gets dumped right there. And so it becomes a maintenance issue. They have to go in and dredge to maintain flood conveyance. Infrastructure repairs become an issue. Downstream of culverts, often you'll see a scour pool form as flow comes blasting out of those pipes and over the road in this case, and this pool will form, and sometimes it will end up undermining the structure. Utilities historically have been put in stream corridors for gravity reasons, especially gravity fed systems. It's the low spot, so it makes sense to put it there. However, they cause a lot of problems. They become obstructions in the creek themselves, the structures do, and the utilities themselves start to be exposed in the banks due to erosion. So LeeAnne is going to talk about, now that we know all of these problems, what can we do that's different? Should we take questions now?
I think we're just gonna wait till the end to manage the questions. I mean, unless you guys want to. We don't want to. We just have to repeat it so that the people on Zoom can hear. Did you have a question, Rachel?
Yes, because you mentioned that the infrastructure for the utilities affected the stream bank, so I'm wondering, like how they're doing the triple tier on 281 North because of the fiber optic demand. Is that just going to completely eliminate this problem in the future, you think?
I really don't know the answer to that particular problem, that,
Oh, you can you just repeat it real quick so they know what the question was?
okay. The I-35 corridor and the triple stack and the fiber optics utilities that are currently a problem apparently. And what, keeping fiber optics out of the stream corridor, is that we're putting them on the bridges, would that fix the problem?
Because what they're doing is, that's why they're making it triple tier. Here is actually embedding the utilities in the different layers of the highway.
That would probably
Now,
help. That is a good solution to keep it out of the creek.
Just repeat that solution.
Okay, forgive me. The follow-up to the question was, is that using the triple tier, they're actually embedding the fiber optic cables in the highway structure itself. And so that will lift it up out of the creek.
And where is it?
281 North from 1604.
Okay.
I-35, 281 north, 281 north from 1604.
And there was one earlier question, if someone you listed objectives and they went a little too fast for them.
Oh.
So I don't know if we want to just do a refresher on that right now or
Well, I can wing it.
stay with it.
Okay.
Yes, awesome.
So the objective of the presentation was to demonstrate the correlation between natural stream processes and what you're seeing on the ground. Identify design practices that can be improved, and also identify maintenance practices that can be changed.
Thank you.
All right. So I'm going to spend the next little bit just talking about what we can do as stream practitioners to hopefully avoid a lot of those things that Tami talked about. I'm going to focus mainly on one specific design approach called natural channel design. We sometimes call that NCD. You may hear that on a quiz later, natural channel design. So really the basis and the goal of natural channel design, like Tami said, is to come up with that channel dimension, pattern, and profile that's appropriate for the drainage area and the topography. And we do that to come up with a stable reach. So hopefully we can just avoid typical maintenance practices that I think we've all kind of accepted that kind of come along with designed channels. So typically, we're working in an actual stream or the corridor adjacent to the stream. So we don't have a lot of opportunities to impact the hydrology of the watershed, but we do have those point source, those runoff from the street and storm sewer systems that are often coming into our project area, maybe in a park setting. So we will use things like low impact development techniques and try to run to try to make a stormwater outfall flow through something like a bioswale or over a vegetated filter strip to allow that water to slow down and infiltrate and some of those pollutants to settle out before it gets to the receiving stream. Okay, so when we are kind of in the design process, we think about the channel geometry and the plan form. So that top picture is a cross section, like the geometry of a natural channel. And then the picture on the right is the plan form, like if we were looking down in a bird's eye view. And you can see that natural channel, there's a lot of variation in that shape. There's a low flow channel that conveys just the base flow. Then there's something that's called the bank full channel, and that really conveys the storms that happen on a pretty frequent basis every 1 to 2 years. And that bank full dimension and area is really the basis of design for natural channel design. It gets pretty technical, but that's like a design parameter that we use. And then there's the larger part of that cross section, that's the floodplain. That is probably what we typically think of whenever we think of a channel floodplain, like the 100-year flow, a floodplain that's 100 feet wide, 200 feet wide. So we're thinking about all of those flow regimes whenever we're designing a project. But traditionally, like in a channelized stream, that shape of that cross cross section is uniform across all of those flow profiles. So you just start stacking water on top of each other. And whenever you do that, you start to see increases in velocities and shear stresses. And so while that may be efficient to get a lot of water out of an area, that's kind of why we have to come back in and maintain these channels, is because the water wants to move. It needs to dissipate that energy either laterally or vertically. And when we put it in a confined shape like that in a straight slope, like Tami said, it can be very destructive as it tries to find its balance. Another thing, we consider in our designs is the profile. And so if we're designing a meandering stream, we will put in ripple pool sequences to allow that energy dissipation, or if it's a straighter stream, we'll put in structures to create that vertical fall to allow it to dissipate the energy. And we'll talk about what those structures are that we can put in the stream to achieve that kind of natural profile. So these in-stream structures have different purposes. Sometimes we want them to just hold the grade or hold the elevation of that channel. Sometimes we want them to provide extra lateral stability on the banks where it's needed. But in all cases, we're thinking about energy dissipation, and just through like inherently having a variety of in-stream structures, you're creating a lot of different habitat conditions for different species. Looking at the top, I don't know if y'all how well you can see it, but the one with the yellow flowers, that's what we call a constructed riffle. So it may not look like much, but it's actually a designed section that's supposed to have shallow water flowing faster, and that is protecting the channel from erosion. And a lot of times that'll be kind of upstream of a structure that's in one of those lower pictures. And that is something that we call a J-hook, and we use it to get the water off of the bank, those erosive forces, into the center of the channel. And I'll show you some other pictures in a minute, but these are just kind of some of the tools in our toolbox. And so grade control, it can look like a lot of different things. In that traditional design picture, that structure is intended to hold an elevation of that stream. It's very hard, and maybe it serves the purpose for those stream conditions, but we can achieve the same thing using this natural channel design approach with these in-stream structures. So this is one of the structures, and I think it'll make more sense once you see a picture in a minute, but this is a typical detail you would see in our engineering construction plans of a cross vein. And if we look at that picture kind of in the upper right, this is a plan view, like we're looking down on the structure. The arrow shows the direction of the water kind of going from the top of the page to the bottom. And so this cross section is constructed out of two arms that are made out of stacked boulders. And then it's connected in the middle by what we call header rocks. Those header rocks are constructed flush with the bottom of the channel elevation. And then there's a scour pool in the center there. I don't think this will show up, will it? No, okay.
You might be able to use your
Okay, so just
cursor here.
the elements. These are what we call the vein arms. This is the header rocks, and this is a scour pool, and the water is flowing over the structure this way. And so here's a picture with the water flowing from left to right. And the way that these structures function is, as the water starts to rise in the creek, you can see that these arms are going up in the downstream direction. So water always wants to take the path of least resistance. So as it starts to flow on the, from the sides of the channel here, it's going to flow perpendicular to these rocks into the constructed scour pool. Oopsie. Okay. And so what that does is the header rock is providing the grade control, like holding the elevation of our channel. And we don't want those erosive forces on the banks. So we're directing that water to the center, letting it dissipate its energy in that configuration. Here's another example, and this has a better view of the pool, a constructed pool. And you can also see that the header here, the head rocks, these are, they're flush with the channel invert. We're not creating a backwater situation. A lot of people think this is going to back up water, but it doesn't. And so in this situation, the water would kind of flow up here on the bank. If that's showing up, yeah, and going across the rocks into the scour pool. So this is a similar in-stream structure. It kind of looks like half of a cross vein. But it kind of depends on where we place this in the stream would determine if we would do a cross vein or a J-hook. So very similar concept, but we would use this where there's a turn in the river, a meander in the river, where we would try to get that water, instead of going on that, what would be like a high bank or a cut bank on the outside of a meander bend, it's going to roll over that rock arm and it's going to go back into the center of the channel. So again, we're providing bank protection, giving the stream a way to dissipate its energy. And depending on, I guess, the radius or the size of that turn, we may need two structures. So here the water is flowing in a different direction, but you can see another J-hook downstream.
So the place where it might cut, you're actually directing it towards the middle so it can't make that cut.
Correct. Mhm.
Both by direction and by
The angle of the arms.
the angle, okay.
Yeah, so all of these, so the size of this structure is kind of based on a bankful dimension. And then there's a certain angle of the arm that we need to get right for it to function properly. And this part of the structure for the cross vein and the J-hook, we call the catcher's mitt, because as the water starts to go up in the bank, it slows down a little bit, sediment starts to deposit and vegetation will grow, and we want that. So that's a good thing. But then also it'll make that water go, not the vegetation and sediment won't, but just the angle of the arm makes that water go over the rocks into that scour pool. So bank protection is another reason why we would use a natural channel design approach. And it could look like in traditional design, they might hard armor the whole channel using concrete, large boulders, grouted large boulders, gabion baskets. And like Tami said, sometimes that might be the best solution. If you're just super confined, super urban, got properties right up to the edge, that might be what you have to do. But we can also achieve all of those project goals in natural channel design using things like J-hooks and bioengineering, which we'll talk about in a little bit. So ways that this picture was shown earlier, traditional practices that we see, especially in park settings, are mowing to the edge of the bank, removal of all woody plants. There might be one grass species there, and they could do this maybe for a variety of reasons. But, whenever you remove the plants, you're removing that root system. So there's nothing to hold that dirt together. So we start seeing bank instabilities, which contributes to a loss of habitat diversity and leads to water quality issues. Without a riparian buffer, we have no shade. So we have increased water temperatures. We'll have decreased dissolved oxygen, algal blooms, just a lot of things that are influenced by that loss of riparian buffer and traditional vegetation management practices. So as part of our designs, vegetation is really an integral element. We always consult with local experts as needed. And we want to pick the plants that are appropriate for where they are in proximity to the stream or out in the overbanks in the floodplain area. And we choose species that will provide that erosion control, the habitat, and hopefully to restore water quality functions, just to spend depending on the goals of the project. Often we can harvest woody material on site if we're doing any kind of realignment where we have to take any trees out. We may be able to use that material on site in some of our bioengineering structures. And then typically kind of on the bank of the top of the bank, and then in that riparian floodplain area, bare root transplanted trees would be used to start establishing that riparian buffer again. So in terms of natural channel design, bioengineering really just means a specialized use of plant materials to stabilize stream banks. And the goal of these structures is really just to get vegetation established quickly. So we build them in a way knowing that in the long term, the bank stability is going to come from the vegetation that's sticking out into the channel and the root mass in the banks. So this is a structure we call a geolift, and this is on the project that I'll show you here in a little bit. But so what these are just soil lifts. We kind of just call them soil burritos. We get a layer of soil, wrap it in this core fiber, and in between those you stick live cuttings, in this case willows, to hold them in place until they just start getting established and propagate. And so those branches and leaves out into the bank are kind of like a flexible armor, providing that protection. And then that root mass in the banks is providing that structural stability to provide that bank protection. And over time, just as that root mass gets denser and denser, that's what's going to provide the bank protection. We also establish riparian buffers in our projects. A lot of times we're really trying to create that stable channel section. So we want the, oh, it's already, oh, okay, 8 minutes or is it 8 o'clock? 8 minutes. Okay, all right, then I'm gonna go a little faster. Okay, yeah, so the benefits of riparian buffers in our designs is really just to kind of provide that structural support in our stream corridor. Other benefits are it allows the waters flowing to the creek to spread out, soak in, and also to store that water in the floodplain to reduce flooding. Depending on the goals of your project, you might have different riparian width requirements. If it's just stabilization or you're in a confined area, we would like to see at least 20 feet on each side. But if you have wildlife or species goals or water quality protection goals, that buffer width is going to need to increase significantly. Like Tami said, this is really another place that we have an opportunity to kind of do roadway crossings better. A lot of times you'll see, like she said, a stream corridor will also all of a sudden become super wide at a roadway crossing. When that happens, the water slows down, all the sediment drops out. You get that aggradation, the accumulation of sediment, which is a maintenance issue, and a flood conveyance issue. Or you may see a really wide floodplain that they've tried to shrink down and force all that water into one culvert. And so there you get really high exit velocities, downstream erosion, which is a maintenance or a repair issue. So one way to address this is to maybe have a series of culverts and have that culvert in the middle try to be the same size as that bank full channel, and at a lower elevation, actually the elevation of your bank full channel, so that during base flow and bank full flows, the stream can maintain that power to move the water and sediment through that crossing. And then as the floodwaters increase, when you have higher storm events, you have those other culverts kind of on that bank full bench that can drain the overbank areas. Okay, this is a pilot project that we're very proud of for different reasons. We worked on it kind of all in different aspects. This is the East Saltrio Creek Restoration Project on the northeast side of town. Here is kind of a more zoomed in area. The project location is actually on the Judson High School campus. That's near Randolph Air Force Base. The forum is kind of at the top of the watershed. The red outline there is the contributing drainage area. It's about 8 square miles. There's also a Martinez Dam 5 that controls part of that watershed. I looked at the aerials today, and there's only a few spots in there that have not been developed over the last 10 years. This project was constructed in 2011. So this project was in a FEMA floodplain. So just as part of that, we had to do a lot of modeling to make sure we didn't impact water surface elevations and to meet FEMA permit requirements. The yellow line just shows the limits of our project, where it started and where it ends. Water is flowing from the top of the screen to the bottom. On the left side is the Judson High School, and on the right side is the Judson Middle School. So this stream was in pretty bad shape. That picture at the top is a concrete drainage channel. That is a concrete trapezoidal channel, like you were saying. It unfortunately entered the stream right on the outside of a meander bend, kind of where those erosive forces tend to occur. So it became, the end of it became completely exposed. The second picture, you can see that the tall shear banks that were present in a good part of that reach. And then there's a picture missing, but that is another bank that was eroding, that was moving laterally towards that road on the Judson High School campus, which was a main road where the buses would go from Schaefer Road to the bus parking area, kind of at the top of the screen there. Here's a more zoomed in picture over on the right, kind of underneath the world map. You can, that's where that concrete channel came into East Saltrio Creek. You can see the proximity to the baseball field there. I think by the time this project was constructed, that fence post was dangling over the channel because it had moved over so much. And then you can see that other meander bend. It looks kind of white right here. So this was an unstable bank that was eroding and moving closer to that roadway. And it looks white because the maintenance practice or the repair practice at the time was to put rock cobbles on that area that were not that big and really only stayed in place until it rained. So it was a Band-Aid fix. Okay, so why the stream looked the way it did is you saw that watershed. It was essentially built out at the time. I mean, now it's very close to being built out. It was modified. There was a dam controlling a good portion of that watershed. The schools, the maintenance practices at the time were to mow to the edge of the creek. So there was no riparian buffer. There was a moderate incision. So that just means it was eroding vertically down, but severe lateral bank erosion that was starting to endanger the road. Kind of in that middle picture on the left, you can see that storm sewer, let me see the sewer manhole sticking out, and the athletic field was being threatened. And it was also for the district a big safety concern because students would walk between the two campuses to get to activities throughout the day in a very unsafe environment. So some of the structures that were incorporated into the project are something that's called a root wad that kind of is what it sounds like. It's a mix of brush, live cuttings, soil, and dirt, but its function is to dissipate energy. And let's see, we have a cross vein down here. It's flowing away from us. There's a constructed riffle that looks like it's going into a J-hook. And then on the bottom, I think that was the first J-hook ever constructed in San Antonio, right? So, also, bioengineering techniques that were implemented were the geolift that we saw earlier, and then tow wood. The stream was slightly realigned, so we had to dig out a new channel in some parts. So there was a source of wood on site. And I believe all of that or most of that got reused into the bioengineering structures on site. Let's see, on the bottom left, you can see that culvert outfall structure and that orange fence. Behind that orange construction fencing is that road that leads to the bus parking area. So that there was a stormwater outfall there that we put in a drop structure. So now it created this offline pool. So now water flows to this offline pool. In low flow, it stays in this pool, and then in higher flows, it will reconnect with the stream downstream. The upper right, that is that concrete channel that flowed from the middle school. We designed and sized a plunge pool that would be appropriate to handle and provided an area to scour out, and then it flows through a ripple and then connects to the main stem. And then on the bottom, it's kind of hard to see, but there was another stormwater outfall that stormwater was treated through a series of bioswales, which are just depressed areas with a lot of vegetation that kind of uptake the pollutants, give it a chance to infiltrate. clean up that water a little bit before it gets to the main East Salvatrio Creek. This is an example of the before conditions on the left. There's an eroding kind of sheer bank there, and tow wood was used in this situation. This is in January, so the vegetation's dormant or dead, but you can't see it. And that's really kind of the goal of all of these projects, is that we don't want you to think that a project was done there. We just want you to think it looks like a natural stream. And to go out there today, it's wild and woolly, and it looks really good. Well, I haven't been out there lately. I hope it looks good. Here's a picture of the tow wood construction. These are some footer logs that are going in, and you'll notice on the left, they still have their root wads attached. So that provides energy dissipation, but it's also really good aquatic habitat. And those will be submerged. A lot of these structures that we're using with wood, we would only want to use in streams that would cover up that wood either all or almost all of the time so that it doesn't rot. And here are Sarah Cruz doing the planting in this area of the tow wood, putting in live roots, a seed mix, and a buffalo grass sod. The tow wood construction is, that structure is below the water line, so you can't see it. So here's a before and after stream alignment. There's really not much change. Except this is where that concrete channel came out and it entered on the meander bend. Here's where that meander bend swung out close to the road. Post project, here's that concrete channel that goes through a scour pool before it enters the main stem. And then here's that offline pool that will reconnect with the stream here.
You said you worked with Sarah, so I know you're a private business.
Right now, yes.
So you work with the city and Sarah on some other projects.
Yeah. Mhm.
Because we have severe drainage. I live in Sherryville. Behind that HEB on West Avenue, it's just a canyon of concrete.
Yeah.
You see the stream trying to be a stream.
Mhm.
And every year they come through and just pull those all out. That's in that future plans or that.
Well, I mean,
I'm sure you
sure, we would love to do that. It really kind of depends on the agency and their goals. If their mission is flood control and they have a budget, it may be hard to steer the ship, but we have done some other projects with the city where we presented different alternatives and they've been, open to it, and hopefully some of those will be getting built here soon. Yeah, most of our clients are government agencies, cities, Sarah, those types of agencies. You can kind of see in the top right, there's some bollards. And so their bollards were put in place to delineate kind of a no maintenance zone. So the school maintenance crews could do their regular mowing up to those bollards, just wooden posts in the ground. And then they were supposed to not do any kind of maintenance in between for that whole stream corridor. And that stream was protected by a conservation easement. So the result of this project is protected the infrastructure. We now have a balanced sediment transport regime through there, a safer environment for the kids. It lowered the maintenance costs. So now they have a much smaller area to mow and they're not going in there and dumping rock on that one bend. So they've significantly lowered maintenance cost. A whole team of Sarah staff was involved in learning the engineering design, picking out the vegetation, they actually learned to do the construction. They've done the monitoring and replanting. So it was a big training effort for Sarah staff. Improved the natural aesthetics, improved the habitat, created a living laboratory that some of the classrooms there could take students out to for different curriculum, enhance the water quality. And just as a kind of a side benefit of the modeling, it actually showed a lower 100-year water surface elevation for the FEMA requirements. So that was a pilot project for Sarah's stream restoration project. It's been in the ground 10 years. There's a video on their website that kind of talks about it. So I think at this point we are done, hopefully in time for questions.
And we do have some questions from online, if I can go through those first, if that's okay.
Okay, so first question is, how do these structures work in large events with intense velocities?
Okay. They work the same. Essentially, when you get to the larger events, the structures are basically swallowed up by the storm event. But just like a natural stream that has the correct dimensions, when the storm goes away, those structures, they preserve and they stay in place, and they keep the channel shape the way that it's supposed to be. So they continue to function the way they're supposed to, even though they're inundated with water.
Okay, next question. Is there a maximum velocity where these can be used in an urban area?
That would be how the maximum velocity is determined by your maximum material size. So if you can get a boulder that's big enough to stay in place, then you can use it. And that sometimes comes down to cost too, but
May also depend on
Yeah.
what the city will allow.
correct. There are certain criteria where they don't want you to go above a certain velocity for safety reasons.
Thank you. Okay, this one kind of is a long one. So, in light of increased risk and incidents of extreme events now and in the coming decades, and the implications that climate change takes away our certainty that historic experience can inform our design standards, could you talk a bit about how you incorporate natural disaster risk reduction concerns into the design?
I can tell you that in urban settings in particular, we generally oversize our bankful channel to account for increases in flows and those sorts of changes. And also it allows the channel to adjust on its own to account for those kinds of changes. That is essentially how we account for that at this time.
And also that bank full dimension is based on a storm event that happens every 1 to 2 years. So as climate change, or as urbanization happens, that amount of water may happen more frequently, and kind of probably similarly in this case. So the amount of water just may come at a different interval than statistically. it
Can I
comes
ask a
now.
follow-up question? So I'm thinking that it's kind of a follow-up question to that. We're in a drought right now, and later on, it will be out of the drought and will be a very big rain. So is this a big problem, designing for no water, nothing in the stream to flooded streams, those extremes that we see?
East Alatrio, the demonstration project, is actually a good example. Right after we constructed it, we went through a drought. And prior to the project, the stream would dry up. Post-project, there was water in the pools, even when the rest of the stream was dry. So one thing we can say is that if you have that floodplain reconnected, your channel reconnected with the floodplain, sometimes you'll actually help with preserving water in those pools. The other thing is that whether the channel is dry or whether it has flow in it, that dimension is there, the pattern is there for when you do have flows. So the other things that we consider is, like, if you're in an ephemeral stream or a stream that only gets water when it rains, you wouldn't use the woody structures because the wood would rot. So that kind of stuff comes into consideration depending on what kind of stream you're in. You would use more rock, essentially.
Thank you. Okay, there's one more, and it's actually from someone in the room, but she's on chat here. So Rachel Sneaky over there. And it's got, there's some parts to it. So how will existing waterways with good design likely be impacted by A, climate change, B, habitat destruction, C, increased impervious surfaces and development, and D, large turfgrass lawns? How will existing waterways with good design be impacted by those things?
Well, hopefully they can withstand all of those things if we've taken those things into account in our design. If it's an urban setting, we consider percent impervious. We look at, is the water already built out? Is it partially built out? Can we anticipate more build out coming? And how do we accommodate that. Like I said, sometimes we'll make our dimensions a little bit bigger than we would if we were in a rural setting, so to speak. I'm trying to think, what were some of the other ones?
Animals.
Habitat destruction. Increased impervious surfaces in development, large turf grass lawns.
Okay. I know the animal, if we're talking about like deer or some animal, is that what we're talking about? Coming in and eating the animal, eating the plants? I'm not sure what you mean by that.
Habitat destruction is what I think she's, how will they be impacted? I mean, in my take is usually these include planting of native plants and native plant communities. And so
Yes.
you're creating habitat typically with these.
Yes.
So that you're mitigating some of the impacts of habitat loss in other places. There's a lot in that question, Rachel.
Yeah. So our approaches always include improving the stream. I don't think that we've ever done a project where you have the stream that is not in better shape when we're finished, but that's the whole goal of our projects. A lot of our projects are mitigation projects. So there's a mitigation component where you have to do your stream. It has to have these components in order to meet a mitigation permit requirement. So I think we do good with our streams for mitigating habitat destruction, maybe in some other part of the stream elsewhere.
Okay, I think it's your turn, Jerry. Jerry's got a question and you'll probably need to repeat it.
Well, one thing brought up was planting. So we can have a major rain event. It could be 10 inches, 20 inches. It's got the 36, 40 inches in Central Texas. We know there's planting. We know how that works. San Antonio is on the edge of the hill country. So will your structures hold up irregardless of whether it's what level that occurs or not? Or in other words, are you planning for the extreme stream events? Are you planning for the 10? Because Sarah, I've heard years ago, was initially planning for 10-inch events, and or even less, and the engineer said they wouldn't allow us to plan for, at that time, for 20 inches or 30 inches or whatever. So what are y'all doing in terms of looking those extreme events? A hurricane comes up here, we got close to it one time, it could drop 30 inches if it got here at just the right time. So those events are possible. So does your stuff work with 30-inch events?
In theory, they should. Of course, there's a certain threshold.
Give it a
Oh,
summary.
okay, so the question essentially was, do our designs account for a range of larger events? The like hurricane type events that come through.
Right.
And so the answer is we can only design to a certain degree, and then cost becomes an issue. So our structure material size will be based on a range of flows. So we want to make sure that it stays in place at least for the 100-year event. And usually if your channel is designed properly, those larger floods are out on a floodplain. And so you will not get the channel getting plowed out by these huge storms. You have a place for it to go and it'll dissipate energy. However, huge natural disasters, for lack of a better word, sometimes the stream is just going to get damaged.
So
for
what
those
are you
events.
planning about? 10-inch rain law? What do you have what is it now, what you're looking at in terms of rain event size?
Trying to think of what the current 100-year.
Well, we look at everything from bank full, which is that really frequent, 1 to 2 year storm event, usually like a 10-year storm event, 25-year, and a 10-year. That's kind of typically the data that's in standard modeling that we do. As far as how many inches that equates to, I think it's probably still in the 10 to 11 range. They've also kind of come up with more updated information. There used to be one rainfall for like a large geographic area, but now with Atlas 14 is what it's called. It kind of varies slightly around town.
Yeah.
Well, the other question I had was about the invasion of non-native plants in these things, because you're talking about habitat there that Johnson Gray would love to get in, compete with, all kinds of stuff. So you can put in a native system, but if it's invasive grasses, especially, there's all kinds of sorts, you know. What do your projects look like in terms of if somebody spotting this came by and looked at the project, what would they think about that invasive, non-invasive, all that sort of stuff, native?
So the question was about, how do you manage invasives on your site? If you're planting
Yeah.
the native
How much
species
do you
bounty.
see, how do you manage that?
So it also can depend on the goal or the intent of the project. Like Tammy said, some of these are done for mitigation to meet like a Corps of Engineer permit. And those have certain success rate goals. So you have whoever's responsible for the project would have to go in for maybe so many years and make sure that there's the coverage that was in the permit requirements. It may also depend on the owner. If they have staff and resources, and if it's a goal to have that native species coverage, they would have to invest, the time and the labor to go in there and do that selective removal. Yes, I mean, we can't guarantee that.
Well, no,
Yeah,
what's gonna happen, just like water does its thing,
yeah,
let's do their thing too. you know,
Right,
and
right.
stuff.
mhm,
And I suspect that some of these here are going to be heavily invaded by non-natives. And it's not the objective, like you said, it's not the objective
right.
of these, but to actually do that. So a lot of these are going to be a lot of invasive plants in there. My guess is.
All our natural areas are subject to invasion by the.
Well, I know, and so, so I'm just thinking of, that's probably not one of the objectives of these kind of projects.
Well, yeah, so it's 8:17, so this has been a great discussion. Thank you guys so much
Thank you
for
very much.
sharing your information with us. And thanks to everybody on Zoom. And we'll see you. There's 30 still on. So thank you, and we'll see you in September.
Thank you. Thanks, everybody.
Good job. That was great.